Hi everyone, this is a second video on the continuous uniform distribution. Um, in this video, we're going to go over some more advanced properties. But before we dive in, let's just review really quickly what a percentile is and the CDF function. So for percentile, we say that some value x of naught is the pth percentile if if the percent of values below x naught is p. Now, typically when we talk about percentiles, we talk about percents. So where you might see it most often is like the SAT, ACT exam is where it becomes kind of a big deal. And if someone says I'm in the 99th percentile, that typically means that they scored better than 99% of other people on the exam. That means their particular score had p percent of if it was the pth percentile, it had p% of values below. So that score is the pth percentile. So that's how we think of percentiles. Now, percentiles have a direct relationship with the CDF function. So if you're thinking proportion or percent of values are below some threshold, that is, again, that is our CDF function, how we define it. Because the CDF is the probability that our random variable is less than or equal to some particular value. So looking about this on a quick graph, the normal distribution is one of the bigger, more important distributions that we typically think about with percentiles. X naught here is the pth percentile, and the values below X naught, there's about p proportion of values below it. Now, I'm being a little bit lazy or imprecise with my wording here because I am switching from percents and percentiles a bit interchangeably, and I'm saying that P is both a proportion and a percent, which is actually not true. But I'm hoping you can forgive that switching back and forth, and hopefully that's not too confusing. Um, but yes, I'm saying Pth percentile, but I typically think of, and we will typically think of proportions instead. Okay, so that CDF function has a relationship with percentiles, where if we plug in a value into that CDF function, so here's the score or value, think of the score you got on an ACT exam, for instance, and you plug it into that function and it pops out the proportion of values that are below that, or the percent of, not percent, but percent divided by 100 of the values below that particular score. So it has this relationship. On the flip side, we could also find the inverse of that function. And if we took the inverse, then the inverse of that function is a function of p, that proportion of value. So if you want to figure out, hey, what score was the 98th percentile, you could put 0.98 in this function and it would pop out the score that was the 98th percentile. So again, we have this nice relationship, which is useful for the discussion we're about to have. Um, all right, one more example as just motivation for these next points. Here are scores. Again, you can have scores that don't have a uniform distribution. Their distribution can be strange, and this often does happen with exams where you will see sort of like humps in the distribution. So you can imagine this. I drew it as a continuous model, but you could also imagine this as like a histogram of scores that appeared on some sort of test where there was really two clusters and nothing in between. And I know I have a little gap here, but let's pretend there's nothing in between. We have two different scores. Someone is the 20th percentile and someone else is the 21st. But because there's nothing in between, these values can be quite far apart, even though their percentiles are nearly the same. And this is something that can happen with percentiles and values in the support or X values. Plotting this as a function of CDF, it looks like the following. So this is the same data or distribution, but on the left I have the PDF and on the right I have the CDF. Again, that function that is returning those proportion of values that are below that threshold. So the x-axis is the same, it is score. And we had that small hump in the beginning, and then we had no values, and then we had more values, an extra cluster. So score 1 that we are looking at is at the 20th percentile. We plug in x1 into that CDF function and we get 0.20. Or we can look at 0.20 and say, hey, here's 0.20, and you are on this x-axis, it maxes, or y-axis, and it maxes out at 1. So you look at 0.20, go, hey, what score was that? And you can kind of look at this function and go, oh, it's right there, and figure out what that x was. And the same with 0.21. So these values are quite close to each other here, but they're really far out over there, and that's something that can happen. Now, percentiles are always between 0 and 100, and you can't get one value to have more or less frequency than another value. There's one 20th percentile, there's one 21st percentile. You might have multiple scores that got, the same score as X2 over here, or as this person. They might have quite a few. But all of those values are still the 21st percentile. So 0.21 and 0.20 happen at the same frequency. So because they happen at the same frequency, we can see that they're actually uniform random variables. It's quite cool that the CDF function, everything that pops out of the CDF function is a proportion of values, right? The proportion of values below some threshold, and it's going to be uniformly distributed, all these values you can have on the y-x-axis. Because of this particular property, given a uniform random variable 0, 1, so any uniform random variable between 0, 1, we can construct a random variable with any continuous distribution that we want, which is a little wild to think about, as you can start from uniform random variables and move to a new distribution, just marking out this way and trying to find out x1 and x2. And you can also do the reverse. So given any continuous distribution, you can construct a uniform 0, 1 random variable. Now that one is a little bit more, I think, direct to see, because you can go here and any value you have on this x-axis, you just look at what its CDF value is, and all the CDFs you get are uniform. So that one feels a little more intuitive, at least to me. So how do you do it? I have these points below. Let u be a uniform 0, 1, and let this inverse function of the CDF of x, I can write little x so we know it's the CDF of x that we're talking about in all of this space. This is x's CDF. So take the inverse function of the CDF of x, plug in that value of u, and it pops out x. Then x is a random variable with the desired CDF that you want. So again, you're starting from uniform. You have all these uniform random variables and you want to generate x, you can follow this process. And then the second point is let x have a CDF f of x. So you're starting with x, and x has this really, really random data. If you plug all that data, it's randomly distributed via x, into its CDF function, the results will be uniform, which is also a super cool property. Now, this makes a lot more sense when you see an example of it in action. So that's going to be the next video. Thanks.